So our next speaker is Luc Damé from University of Paris-Saclay, and he'll be talking about coatings to hopefully improve the reflectivity or non-reflectivity of satellites.
Thank you. Yes, in this talk, we will address the fundamentals of the satellite driver design. We should reduce their brightness, their reflection. And so for that, it's not...
Just 1 second, please.
Okay. So, okay. Well, so it's coming, technology. So we are very pleased to present you today the nanostructure ZNO surface functionalization to combat new space-like pollution of satellites, constellation of small and nano satellites, and most of them that have no steerable solar panels, so that they cannot orient them towards the sun properly, and so there are bad reflection to the Earth and to the observatories on Earth. So it's presented by LATMOS, IPSL, CNRS, University Paris-Saclay, by our university also, and the Observatory Versailles-Saint-Quentin, and Nanovation, that is doing the fantastic deposit by pulse laser deposition of this new material, zinc oxide. Okay, so motivation is that the satellite operation and astronomers are really beginning to explore ways of mitigating sunlight reflections of satellites with technologies to darken satellites. It's important. However, up to now, the efficiency of these classical techniques remain insufficient, and policymakers should implement rapidly a policy option on research into new innovative technologies that further darken satellites' reflection. And for that, we have a proposal. It's the nanostructure ZNO, so zinc oxide, that is a key technology to address this reflection issue of satellite. So since the start in 2019 of the Starlink launch of 60 satellites that were extremely visible in the sky and that made the news, we now have more than 5,000 Starlink satellites, and we should soon have 7,500 more, at least, approved. So the problem, as was mentioned just before by the previous presenter, is that these satellite reflections come from the solar panel and from the chassis of from the structure, mostly aluminum, of this satellite. And they really flare, so they are as visible as Sirius in the sky with high magnitude when they are indeed badly oriented along their travel. So the major aspect is for small satellites indeed without steerable solar panels, but many constellations have no steerable solar panel. So that's really the problem to address. So before presenting the ZNO, I would like to say that we need to have policy decisions, and they are required to progress. As pointed out on Monday by the CPAS Director Piero Benvenuti, one, we need a voluntary mitigation. We need voluntary mitigation measures, stakeholders for studying, implementing the mitigation measures, and to start fundraising on specific projects. Following Karen Howard from GAO, she really made clear that it's time for mitigation measures for light reflections of satellite constellation. We address only the optical part, in fact, of the problem of this constellation. But clearly, we have to address first, and that was, she pointed out, the satellite's design drivers. Rather than trying to suppress all those bad reflection, we can suppress them from the start. Hardware correction is always better than software with much better SN ratio in our case. So policy options to overcome insufficient technology development. There should be more technology development to force the industrial constellation to define standards, have regulation, and get agreement with these industrial. So we proposed back even in 2019 a key technology to mitigate sunlight reflection and improve and get also solar cells efficiency and lifetime. It's these nanostructures and nano coatings for solar cells that could also be applied to metal, so to aluminum and to the chassis of the satellites. So let's find the path to its implementation. So the ZNO nanostructure realization is made by epitaxy. So that's one of the first work. We did it on a silicium base. So it's made by pulse laser deposition by, It's made by pulse laser deposition with a krypton laser going to start atoms from a target that will be zinc oxide in that case, and in a vacuum chamber with some trick in order to get this nanostructure. That is a true picture of the nano structure obtained, so 500 nanometer, about 1.52 micron high cones that are irregularly spaced, which is a big advantage. So in this setup, we can use, for example, 100 millimeter dimensions. It has the PLD, the pulse laser deposition, has a big advantage on the chemical methods, is that it is less defects and a very high crystal quality, very high surface quality. So here, on a bare silicium wafer, you see the reflection, so it's gray, it's reflect. When you add this mod IZNO on it, and the adherence is excellent, was tested, then we have a very black, no reflection, in fact, almost. In fact, it's less than 0.5% reflection, even on very high incidence angle. So we did also that directly on the most used cells, solar panel cells. So the Azure Space one, the 3G30A or 30C, with or without the anti-reflection coating. So these have a cover glass, CMX 100, to protect from radiation. The point is that when we do our nanostructure on this small piece of 1 by 1 centimeter, and we illuminate the solar cell, as you can see, the solar cell is reflecting a lot, but the ZNO is really below this 0.5% reflection, even on very high incidence angle. So it's extremely efficient in reducing this reflection of the solar panel. It can be deposited also on aluminum, so it's really the way to go for this satellite. It's expensive doing it by PLD, by pulse laser deposition, but that's what we need to impose to the satellite constellation companies. But the development of it at the level of the research laboratory has a cost, and it's more costly to do the PLD than to develop the full satellite structure of a 1U or 2U nanosatellite, for example, like what we have done. So there are many satellites and nanosatellites using this Azure Space triple junction solar cells assembly with CMX glass for radiation and an anti-reflection classical interferential coating. In the first step, as we have shown, the nanostructure ZNO, which is very transparent, so it is applied on this small cell with CMX glass, and it has, with or without the anti-reflex coating, and the performance were excellent, this anti-reflection, so 0.5%. Test of homogeneity, test of adherence, etc. have been done, and everything is working fine. So ZNO is also radiation hard and could allow to suppress even, or at least to reduce the CMX protection that is used, this glass of 100 micron that is on the solar cell, in addition to the anti-reflection coating to protect the solar cell from radiation and from debris. So it's a very hard, the zinc oxide is very hard, so it's as hard as the CMX can be, CMX done by the Key Optics company. So in the second step, what we want to do now is to apply this ZNO Mod I coating to a full Azure Space cell. What we can do, because they are 40 by 80 millimeter, so we can use them in our own PLD device, verifying adherence again, homogeneity, and nanoversion facilities can proceed to that very well. Third step, and we want to do that in all the next 2 years, is to go to space qualification, TRL-7, up to a flight on our next nanosatellite, so that it could be even proven by flight, in-flight, TRL-9. So that's the 3 work package for the 2 years. But the important is really the characterization of the properties and performance of the solar cell panels, including radiation protection, outgassing, contamination. It protects from the outgassing also the deposit itself, so it's another advantage. It increased the lifetime and the efficiency of the cell, and in addition to the anti-reflection effect, which is extremely important. One very important thing is that the nanostructure doesn't need to be regular. In fact, it's even a big advantage that we have verified in our realization that the nanostructure are irregularly spaced, as was shown on the little picture before. I could show you more, but it's very important. Second, in terms of cell efficiency, in fact, as you can see, the ZNO here is nanorods and not nano cones like we are using, but it's the same technique to get the two of them. You can see that the efficiency is increased compared to the classical TIO silicium technique of anti-reflection coating. So with the anti-reflection coating in ZNO, we gain in efficiency and so in lifetime also of this solar cell, very used in Europe, made by Azure Space. We have been in the solar irradiance, ultraviolet observation, chromospheric oscillation, interferometry, spectroscopy for many years, and now we also are launching nanosatellites, so one new nanosatellite, on which we did the study on the solar cells, but could not implement it in sufficient time. The second one that was launched earlier this year in April was a 2U system, so not oriented, so with the panel going everywhere. And we have a new one that will be launched in 2 years that will be, that we intend to use a larger one, in fact, for this test of the solar panel cell modified with ZNO coating. So that's just this design of the next satellite that we are proposing at utmost, and that should fly by 25. And as I say, financing is required, and discussion with industry all should engage with other space cells and more, indeed, to get rapidly to a complete demonstration in space of their use, in fact, and anti-reflection power. So conclusion. Conclusion. We have demonstrated the potential of nanostructure, but ZNO coatings for a significant reduction of the sunlight reflection of solar cell, even at high incidence angle up to 80, 90 degree even. So it's better than 0.5. In fact, it's more 0.2%, depending of the quality of the coating that we do. ZNO coating has transparency and radiation threshold. It is a potential advantage for solar cell efficiency and lifetime, and it can be used also as a radiation protection. So we could avoid the CMX 100 glass on the solar cell. So that's why we need to discuss with the industry. ZNO coating could also be used on most of the structure, aluminum in particular, to further darken the satellites. Technology and programmatic goals are determined for the next 2 years to reach TRL-9 and flying on the next UVSQ Latmos satellite. So the new UVSQ sat NG, new generation in 2025, or maybe 26, we'll see. The flight is not reserved yet. So research and development on this disruptive development is already engaged, but pending reasonable financing. That's why we need policy decision. Not compatible with the classical institutional partners. In France, we propose it to CNES, to ANR, to INSU. We propose it in 2019, after we worked on also other technology issue with UV detectors in UVC band. But now we are ready to restart. But at that time, 2019, people were not really still sensitive to the big problem that were causing this constellation. So I think now that it's time to really start the work at the source level, which is the satellite driver, the satellite design itself and its correction. So we propose to INSU, but classical astronomy bodies have no money. When you want to do a PLD deposition on 10 centimeter, it's 20,000 euro worth. So it's more than many of the budget that this company will give. So there is an urgency to establish standards and to discuss with constellation industry their implementation of mitigation measures on their production line before we reach tens of thousands of satellites lightening the sky. So thank you very much.
Thank you. We have time for one question, if we have any. In the back.
Have you made any even rough computation of a thermal model of a full-size satellite? Because it would be great to transform every satellite in a black body, but I wonder what the thermal situation would be at that point.
Well, the coating is applied to the solar panel, so it will indeed change the thermal behavior of the global satellite. So we need to do indeed a thermal modeling complete satellite. What we do for small nano satellite, we have thermal model. We tested, for example, for InspireSat 7 that we just launched. We had a thermal model, and we effectively stand in the plus or minus 5 degree inside, etc. So it's clear that that will have to be done for the Starlink satellite, for example, on their production line to see, to have a definite proper model. This has to be done with them. So we need to have a body asking to provide the data and do the modeling. It's indeed important to do, but we have all the tools to do that. We have modelized satellites for years. I was the PI of Gulf on so of PCAR satellite, microsatellite, etc. So we know how to do that, and it has to be done indeed.
Okay, thank you.
Thank you.